We're working on chapter 3, mean, mode, and median. We covered quite a lot of the stuff on that yesterday. We looked at least how you can use your calculator to find the mean, the mode, and the median. And I believe, didn't we also do the transformation stuff? Like if you doubled all the numbers, wouldn't the mean get doubled? You know, and everything else would get doubled, right? Those kind of things. So we've covered that. What we haven't done, we're going to spend more time on that than this, is how to calculate the mean, mode, and median, but using the software SALT. Right, so we can use our TI-84, which is kind of cool, or we can then use SALT, which you will know which questions you're allowed to do it, because in WebAssign there's a big orange background, white writing says use SALT. So whenever you see that button, you know you'll be able to use SALT. So let's jump right into some of the homework questions and kind of use them as a guide to the kind of things that we're going to be looking at. So who knows what one I want to pick? All right, let's pick this one. In this question, this problem, we're going to explore the effect of a mean, mode, and median on multiplying each of the data values by the same number. So they start off by giving us this data set, which I'm going to write down because it's going to have to disappear in a minute. And it's what? 7, 7, 8, 11, and 15. 7, 7, 8, 11, and 15. And we're going to have to do it either by hand or with a calculator, right? It really doesn't matter which one we use. So let me jump in and do it. Right. So question A says compute. They're doing it in their order, so mode first. The median is second. And then lastly, the mean. And since there's only 5 numbers, can I just do it the boring way? I just do it in my head almost, right? Would you look at these numbers? Would you agree that the number 7 occurs more often than anybody else? So the mode is 7. It was as easy as that. Now, if you want to get the median, thankfully the numbers are in order. And would you agree that that guy there is in the middle? So the median is 8. So I didn't need to do really that much work here. I think the only one I'm going to have to do some kind of work is the mean, right? So I'm going to go 7 add 7 is 14. That's 22. That's 33. That's 48. And I'll go and I'll do 48 divided by 5 numbers. And I got the answer 9.6, which again, it wasn't that bad, right? I didn't need to do that data stuff. You know, the one we showed you yesterday where you typed in the data and you did all sorts of things. When a small list of numbers, it's not worth that. Now, in question B, they said, multiply each of these data values by 4. So that's going to be 28, 28, 32, 44, and then finally 60. And then it asks us to find the mode, the median, and lastly, the mean. Well, I know the mode, I know what the median is, and I know what the mean is. Now, couldn't I just pretend that that question didn't exist and get the answer just by hand, right? Straight from scratch. Now, if I did it that way, wouldn't the mode be 28 again? Wouldn't the median be the guy in the middle? And wouldn't the mean be what you got if you added these all up and divided by 5? And I'm going to cheat a little bit here, and I'm going to do 38.4. Are you comfortable that we could have done that simply just by using the new data set? Couldn't we also do it a different way? Couldn't I use these numbers to predict these guys? Right? If you take a data set and you multiply all the numbers by 4, doesn't the mode, the median, and the mean also get multiplied by 4? And that would be, I don't know, is that a slightly quicker way of coming up with the answer? I guess so. This question was actually designed to show you that that was the property, right? but we already know that that's a property because we looked at those questions yesterday. And then I'm going to have to show you the rest because it's picking choices here. Right, so here we go. Compare the results to A and B. Remember the top three numbers and then what we did when we multiplied it by 4. And it goes in, it gives us some observations. So compare the results to A and B. In general, how do you think the mode, the median, and the mean are affected when you multiply the data set by some constant amount? In this case, it was 4, and they're calling it C, right? Multiply each data value by the constant C results in the mode, median, and median increasing by a factor of C. That one says they stay the same. That one says they decrease. And that one says there's no distinct pattern. Would you agree the one that works is that one, right? That's their way of phrasing it. Now, suppose you have information about the average height of a random sample of airline passengers, and you're told that the mode was 67 inches, that the mean was 72 inches, and that the mean was 65, right? They don't tell you the data, they just tell you those 3 statistics, right? The mean, mode, and median, right? Suppose you want to convert this data into centimeters. And if you didn't know that, the way you convert inches into centimeters is you multiply it by 2.54. What are the values then for the mode, the median, and the mean now? Well, if you take 67 inches and you multiply it by 2.54, that would be 170.18 centimeters. Do you see? I know what the mode is, even although I don't know all the data. Isn't it just the same answer in inches multiplied by 2.54, which gives you the answer in centimeters? Now, if I take the second one, which is 72, and that happens to be the median, I believe, and you multiply that also by 2.54, you get 182.88. And last but not least, the third one, which is what, 65 inches, and you multiply that by 2.54, you get 165.1. Cool. So if I give you a data set, you should be able to find the mean, mode, and median. If we say add 10 to it or multiply it by 2, shouldn't you be able to calculate these guys? They're a little sentence saying what's going on. And in this case, if I give you the mean, mode, and median and tell you that we're going to multiply it by 2.54, then you just multiply the 3 numbers by 2.54, right? This one by 2.54 gets you that guy. This one by 2.54 gets you this one. And lastly, that one by 2.54 gets you that one. And can you see question 8 kind of does virtually the same kind of thing, right? And question 9 is solved. So let's pause on that. And I want to do some stuff at the top just to get these out of the way. Actually, I think I did this question. Yes, I did question 1. And I'm pretty sure I did 2. Okay, this one I don't recollect doing, so let's get this one out of the way. Suppose you've got a data set that has at least 3 numbers in it. Okay. Suppose the highest value is increased by 10, right? So whatever the number at the end is, you added 10, but only to that number, right? Just the one at the end. And the smallest number, right? You found that guy and you added, and you decreased it by 10, right? So the big number became 10 more, the small number became 10 less, right? We should be able to answer these questions then. Would the mean change? If you added 10 to the big number and you took away 10 from the small number, would the mean change? Yes or no? What's your answer? Yes or no?
Would it be no, because the sum of the data is still the same?
You are bang on. That's exactly the reason. Now, would the number in the middle change? Right, so you've got the same data set. You just changed this guy at the end to made them 10 bigger, and this one you made them 10 less. Would the number in the middle, the median, change? You're shaking your head, so you're correct, Brandon. No, it won't change. And the reason it won't change is the extreme values do not affect the median. Remember, the numbers at the end don't affect the median, right? The guy in the middle is still the guy in the middle, whether the guy at the end is 40 or 4,000, right? He's still, the middle guy is still the middle. Now, this one here I would argue with, but I'll tell you what their answer is, just to get it over with. Does the mode change? And they went and said, yes, it could change. And it's depending on which data values occur most frequently. I'd argue about that, but just pick yes to get the points and get it out of the way. The reason why I'd argue about it is that if 7 was the most common number and you added 10 to the biggest number, I don't know how that's going to make 7 less common, right? Would you agree? If 7, I'm picking 7 at random. So I would disagree with the answer, but we've got to do what they got to do. Now, the last question that they have at the beginning, just to get this out of the way, when a distribution is mound-shaped, right? Uniform, single hill, symmetric, all that good stuff. What is the general relationship between the mean, the median, and the mode? Right, so if the data had a nice hill right in the middle, nice and symmetric, what do you think the mean, mode, and median are likely to be? What's the relationship between them? Here's your choices. Any guesses? Any takers? Last chance. Would it surprise you to know that they're all the same? Because that's what you get. If it's a single hill, wouldn't the middle number probably be in the middle where the hill is, right? If it's a nice symmetric hill, wouldn't the mean be in the middle? Right? Wouldn't the most likely number be probably in the middle for the same 3 reasons? So they're all essentially likely to be equal to each other. So this takes us to the last piece of the stuff. This section's pretty much finished, which is we are now going to show you how to use SALT to calculate mean, mode, and median. Well, technically, you can only use SALT to get the median and the mean. SALT doesn't find the mode for you. So here is a very small set of data. Would you agree that we could get that answer just by doing calculator, right? We really don't need SALT, but just so you get used to using SALT with bigger data sets. Now, in this question here, would you agree the most common number is 2? This data set. There's more 2s than anybody else. Right, now how do you use SALT? First thing is you click SALT, and I'll show you what happens. That appears. And you see your data set? There's your 5 numbers. Now we want to get the mean and the median, right? Those 2 we do want to get. So go to this heading here called descriptive statistics and click on it. And the mean is 4.6 and the median is 3. Right? They tell you lots of other cool stuff, but right now we're only interested in what's the mean, 4.6, and what's the median, 3. So 4.6, oops, wrong way around. The median is 3 and the mean was 4.6. Right, now for 5 numbers, that's not a big deal. But can you imagine the data set had 50 numbers in it? Wouldn't it be great if you just could hit the solve button and do that menu and, you know, the answer's there in front of you. So for big data sets, it's worth it. Now, you're going to multiply each of the data sets by 2 and then recalculate them. Now, I'm going to show you how you would do it in SALT, and then we can look at how we could do it even quicker. So I'm going to go back to my data set, and they said you're going to, let's check what you're going to do, multiply everybody by 2. So I'm going to click on that guy and make him 4. Going to click on that guy and make him 4. I'm going to click on this guy, double him and make him 6 to the last 2 guys, double this guy to 12, and finally double this guy, oops, double this guy to 20. So our data has now been doubled. I can then go to descriptive statistics, and you see that the mean is now 9.2 and the median is 6. So that guy is 6. That guy there is 9.2. And what would the mode be if you doubled all the numbers?
Before?
Before. In fact, since we know the property that if you double the data, don't you double these 3 statistics? Couldn't have just doubled them and saved a little bit of time and not bother to solve. And they ask you the same kinds of questions before, and then actually that looks like almost a duplicate, just with slightly different numbers. Suppose you were told the mean, mode, and median, and you wanted to turn them into centimeters. Remember that 2.54 thing that we did a little minute ago? There's just another version of it with 3 new numbers. And question 9, you can do the same. And here's something a little bit better. Mean, mode, and median. And here is our data set. See it there? I want to get the mean and the median. So I'll hit use SALT. Here we go. Okay, it's not too bad. And descriptive statistics. And the mean is that guy. And the median is that guy. So I'm going to do the mean, copy it, put it in there. The median, I think it was 3. Let's check. What was the median? Median was 5. Okay, put that guy in there. And the mode, well, you just have to do that the good old-fashioned way. Tell me if I'm wrong, but I think there's more 6s than any other number. Does that seem reasonable? I can see 3 6s. Is there anything that there's 4 of something? Right. And I'm going to assume then that I found the right guy.
There are 4 6s actually.
Even better. Right. You're right. I missed that one. And so that counts as the mode. But would you agree this time it was worth it? Would you agree using the SALT button actually saves you some work, right? Because if you had to do that by hand, wouldn't you have to rewrite them again first in order, just so you could figure out where the middle number was to get that median of 5? And if you wanted to get the mean, wouldn't you have to do a fair amount of work as well to do that? So it did work. Now, question 11, SALT is getting even more useful. Would you agree that even that would be onerous on the TI-84? Wouldn't you have to type in a lot of numbers and make sure you didn't type in 42 when you meant to type in 24? Or what else goes wrong when I do it? I miss numbers when I type in a lot of data, right? I just skip one and just forget where it is. So how old are professional football players? The 11th edition of Pro Football Encyclopedia. I never even knew there was such a book. Did any of you ever heard of that book? It's probably those books that, people who love numbers in sport, the kind of baseball guys who can tell you the batting average of Hugh Smith in 1950, those kind of really into that kind of stuff. That's probably the kind of book they would own, right? But We don't own that. So this 11th edition of it gave the following information about, and this is a random sample. So it's not every football player. It's just, you know, a random sample. I'm not really sure how many. What's 1, 2, 3, 4, 5, 6, 7, 8, 40 of 40 players. And we are going to find out what the average age of professional football players is. Anybody got a gut feeling? How old do you think? I'm saying 26. That's my number. Anybody want another number? I'm guessing.
We'll go with 24.
So you think a lot of professional players tend to be quite young because they don't get many seasons, right? You know, it's a very physical job. You know, they get hurt easily, or once they've made a couple of million, they don't want to risk getting hurt, right? Whatever. Let's find out. So I hit the button, and this guy collects all the data for us. And I want to know the mean. And am I good or am I good? That was a guess, by the way. The average age, the mean age is 26.25, at least from that sample. And the median was 25.5. So I'll go in here and do a 25.5, and the mean was a 26.25, and the mode, oh, I wish the mode would leave the building by now, because it really should. Because it's a pain in the butt, isn't it, to get a mode? So tell me, what age in that list is the biggest, happens the most often? I'm looking at a whole load of 22s down that column, but that could be just 22s. I'm picking 22s right now. Can anybody find a year that there's more than 23 people with that age? Oh, there's 4 22s. I'm even more comfortable about 22 now.
26.
Oh, shoot. So I missed it. How many 26s are there?
I also count 4, but I think there might
Oh, okay. How many, do another scan on the 22s. How many 22s are there?
Oh, the answer is 25. There's 6, 25.
25, there are even more. Okay, 1, 2, 3, 4, 5. Okay, thank goodness. We got a winner, right? There's more 25-year-olds than anybody else. So far, so good? Right, now, compare these 3 averages. All of these are called averages. Does one seem to represent the age of football players more accurately? And explain why. Well, the averages are very close. Would you agree that these 3 numbers are not miles apart, right? So the averages are very close, is this one. The averages are far apart, no. The averages are very close, is that one, right? So I'm only going to pick either dot 1 or dot 3. Now in dot 1, the averages are very close, and the mean seems to represent the ages more accurately. And this one says the averages are very close, and it's a median. Well, I know which one I'm picking. Should you pick a mean or a median in a data set that looks like this? Who basically represents the typical football player? The mean of them or the median? Who am I picking? Come on, you have a 50-50 chance, and even if you're wrong, I'll just make a fool of you, right? I'll just get everybody to point fingers and laugh at you, right? That's how we do this class, isn't it?
I
Would
would
be the mode.
It would be the median, because the mean would carry extreme outliers in it as well for the calculation.
Yeah, that's the answer I was hoping for. That's like the textbook answer. Pick a median. It tends to be unaffected by extreme things. Could you imagine there might be a quarterback? No, God. Couldn't there be a kicker who's like 48 and still kicking? You know, the guy, all he does is kick the ball, right? Wouldn't he screw up the numbers? Wouldn't he be a really old guy in the team, right? So pick median is typically the safest. So that's what I'm going with as well. And one last question, which is kind of a curveball because we're on sporting analogies. So here's the curveball. In your biology class, your final grade is based on certain things. It's based on your lab score. I'm writing this down so you'll see it later. And 2 major tests. So I'm going to call that test 1 and test 2. Your lab score is worth 17% of your grade. Each major test is worth 23.5% of your grade. And your final is worth 36%. Okay, now leave, and we are going to try and find out what someone's final percentage would be worth. In fact, that's exactly how I do your finals. Do you know when you look up the syllabus, I say 20% is from homework and 30% is from a midterm and so on and so forth, right? So this is kind of similar. Now, we're going to tell you what this person got, and we're going to combine this information with the scores that they got here to find out what their final grade is. And I'm going to do it in green, so I've got a color scheme going here. This person got 65 in their lab, okay? They got 95 in test 1, they got 67 in test 2, and they got 73 in the final exam. And we have to come up with what is their percentage, right? Their final grade. Did they get an 82% or a 71.3%? Right? And what you do is you take these guys and you calculate them and add them up. So the total grade, or whatever you want to call it, is going to be 7% of the lab score plus 23.5% of test 1 score plus another 23.5% of test 2 score. Of course, I don't have enough room, plus 36% of their final. Okay, so let's see what this particular person is going to get. So it's going to be 7% of 65. Then you add 23.5% of 95. And then you add another 23.5% of 67. Then you add 36% of 73. Are you comfortable with what we're doing here? Right. So if you want to get 7%, it's easier. Yes, Aidan, question.
Sorry, I didn't mean to use the clap thing, but I meant to raise my hand, but
I got what you meant.
Yeah. Isn't that 7% supposed to be a 17%?
Yes, my little bracket killed it. Well caught. Well caught. Yes, it should be 17. I drew a little bracket round my 1 and I killed it, and I didn't notice that I killed it. I'm glad you did. Right, 17% is 65. Type it in as 0.17. That's 17% as a decimal. Then you can do 65. And then add 23.5 is 0.235 times 95. 23.5 is 0.235 times 67. And then add 0.36 times 73. And this person got 75.4%, right? We call them weighted averages if you want to know what their name is, right? So this person would pass. Remember, 75% is a 2.0. So not by much, but right, they can get their AA and walk home and be happy, right? If that's the last class they took. Are you comfortable about that? Now, if you know what your percentage homework is and you know your percentage for your attendance and all those things that I do, you will eventually be able to actually find out what your grade is by doing this calculation, or at least what it is based on what you know, right? But that will fluctuate as the weeks go by. Kind of nice finishing point for this one. Is there anything else you want to know about mean, mode, and median? And before we move on. So we're now going to look at our next section. And it's also, I believe, part of chapter 3. And it should be to do with variation. Let's find out what it's called. Measures of variation. That's it. Let's do some notes then. We're doing sports analogies today. So I'm going to do a sports analogy for you. And if the numbers don't quite make sense, well, you just figure out that I don't know how to do certain sports points, right? Let's suppose that you've got 2 players and they are in your basketball team. And one of the data things that you collect is how many points they score, right? How many points they score on average in a game, right? So they've played for you, for a couple of seasons, so you've got a fair amount of data. And we're going to call them A and B. Now, A is made up of, I'm going to write down some simple numbers here, right? A gets 20 points, 20 points, 30 points, 20 points, and 20 points. So that's his last 5 games, right? So you typically, don't you want to use data that's the most up to date, right? Knowing what he was doing last year isn't really as good as what he did in the last 5 games. You agree? For most players, that's a better indication of how he's working, right? And that means that this particular guy, let me put the numbers in, 20, add 20, add 30, add 20, add 30. I'm just making sure that I get the right number. That person, on average, will score 24 points in a game. Would you agree he's a good player, right? That's a guy you probably want to play in your basketball team, right? 24 points. I'm assuming that's a pretty good score, isn't it? For those who know basketball. Average? Okay. At least you'll play him, right? He's not horrible. Now, the other player, he happens to have this as his score. And he also happens to have an average of 24. So superficially, would you agree that both those players have the same average number of points that you get from them in a game? But if you look more closely, isn't player A much more consistent, right? When you play him, you're pretty much going to get 20 to 30 points off him, right? If you play player B, isn't he much more inconsistent? Doesn't he have really good games? And I wish I hadn't picked them. Not really good games. Would you agree that numbers variation, as we call it, is important? Would you agree if you were choosing someone, knowing how consistent, right, how varied their answer is, that would be a good piece of data to be aware of, right? And I'm pretty sure that, you know, football teams and basketball teams and all these other teams, don't they collect a mound of data on what their players do, right? How many points they score, how many interceptions they get, how many tackles are successful, you know, whatever the position is. Yeah, if you're a kicker, don't they keep track of how many 3-pointers you get and how far you score, right? This guy's really good at 50 yards and all that stuff, right? They collect tons of data. And one of the things I like to collect is how varied things are. So we have a term called variation in statistics. And so very crudely, wouldn't A have a small variation? And player B would have a bigger variation. So I'm just using words right now, but you getting the idea of what variation is? It's a way of saying how spread out the data is, how consistent they are. So even if you have the same mean, couldn't you have totally different variations? And there are 3 measurements of variation. The first one is called the range. The second one is called the standard deviation. And the third one is called the interquartile range. Now, nobody likes saying standard deviation a lot, so we very often just call it SD for short. And nobody likes to write down interquartile range, so we tend to call this guy IQR. And so what we're going to deal with today is how to calculate these 3 different numbers that represent variation, right? How spread out the data is. The bigger this number is, the more spread out the data is, right? The more inconsistent that player is. The smaller that number is, the more consistent they would be. So this guy here might have a standard deviation of 4, and this guy might have a standard deviation of 8, right? You can tell 4 is smaller than 8, so that gives you a good idea. And standard deviation in particular, out of the 3, is the most useful number that we will use in statistics, because there's lots of things you can use this number for to predict other things about your data set that you might not be able to do otherwise. Of course, we're going to have to do it 2 different ways. So the first way is we're going to use a calculator. And we'll show you today how to do that. And after we've done some practice at that, the second way is we're going to show you that you can do it using Solve. You can't easily do these kind of calculations by hand, right? You could probably do the mean, mode, and median by hand. Would you agree? If somebody took your calculator away and there was only 5 or 6 numbers, you could do it, right? You could get those answers. Standard deviation is an extremely ugly calculation that if you ever look at it in the textbook, you'll realize why we don't do it by hand. So you just trust me, you just don't do it. The interquartile range, you could probably get away with it, right? But it's a bit awkward. So it's much easier if we just let the calculator do these things. And so let's jump right into it. How do we get the calculator to find all 3, right? Our range, our standard deviation, and interquartile range. Technically speaking, I've kind of told you a slight lie. when I talked about the calculator. Because we don't actually get the range using it. But don't we not use the calculator to get the mode either? Don't we just eyeball the mode? You can get the range, and that's easy to do. It's just the largest number, take away the smallest. And I'm going to use player A to do that. So we have 20, 20, 30, 20, and 20, right? In this case here, would you agree that the largest number was 30 and the smallest number was 20? So the range would be 10. You comfortable with that? Just scan through, there's the biggest number, scan through, well, lots of them, there's the smallest. Now the calculator. You've actually, you know how to do this. We're just going to get different numbers. Remember we did the mean and the median using the calculator? Remember we typed in the data? We're going to do the exact same process. So I'm going to begin by hitting start button and edit. Oh, I've got an idea. Tell me if this is better. If not, I'll just go back and do my calculator. I don't mind how I'm doing it. Can you see a TI-84 on the screen here? Right. Is that easier than me doing it by fingers, or does it not matter to you? Does anybody have a preference? You don't care. So since it's here, shall I just do this one then? Saves me going back out again. Right, so I'm going to do the view and I'll put in key press history there. So you should be able to see the keys. So pause again. Hit the start button. Choice number 1, edit. On my calculator, L1 is totally clear. You agree? Sometimes don't you have numbers and you have to hit delete, delete, delete to clear the screen. So I'm now going to type in my numbers, which were 20, return, 20 again, return, 30, 20, and 20. Just like we did last time. Hit the start button. Move from edit to the calc by pressing this guy here once. And now we're on one variable statistics, just like the last time. Now on my calculator, because it's a more modern one, do you see that everything's set up? So I just hit enter a lot. For some of you in the older calculator, don't you have to do blue button number 1 and then enter? Right, that's the only difference. So enter, enter, enter. And here we go. Now, there are 2 guys that we need to calculate. There's a standard deviation guy. And I'll tell you where he is. Do you see that guy that has an X, an S, and a little X next to it? Do you see it, this guy here? That's your standard deviation. So your standard deviation is 4.47, at least to 2 decimal places. Now, if you hit this bar here, and you go down, you get a bunch of numbers and they start with min and they finish with max, and you get Q1, Q2, and median, right? You see all these guys here?
Can you make your box bigger so we can see the rest of the keystrokes? Like you're talking, but we can't see all of them.
Oh, I didn't. Don't you do that? Don't you do that? Yes. I should be able to do this guy. There. You see him now?
Yes, thank you.
Right, so let's pretend I didn't know the range was 10. Can you see that I now know what the smallest number is and the biggest? Why would that be important? Well, when it's 5 numbers, it's not. But can you imagine you had to do it with 50 numbers? Wouldn't it be quite hard? Oh God, where's the smallest, right? You'd be scanning forever. Is that a 22? No, there's an 18 and so on. You don't need to. Do you see it tells you big and small? So in this case, it would be 30 take away 20. We've already done that one, but I'm putting it in. The range is biggest, take away smallest, and the answer is 10. And now we have this guy called the interquartile range. It would be really nice if the calculator just told you it, but it doesn't. But it does give you the numbers that you need. The interquartile range is Q3, well, that's going really dark, Q3, which is 25, take away Q1. So 25 take away 20. And so the answer is 5. So to get the interquartile range again, you take the value of Q3, which is called the third quartile, if you want to know its name, and subtract the value of Q1, which is called the first quartile. We comfortable with that? Plug in the numbers and everything is here. Let's return to the screen and show you me using it then. The range, biggest takeaway, smallest, 10. Standard deviation, which in our calculator is called SX, 4.47. And interquartile range is 5. So these 3 different numbers are ways to measure how spread out the data is, right? And out of the 3, the least useful is the range. And one of the reasons why the range is the least useful, isn't the range very susceptible to outliers? Can you imagine you just had one game where you only got no points, right? Well, maybe you get injured, right? Who knows why, right? But wouldn't the range be affected by that, right? It would be affected a lot by just one big number or one small number. So we tend to not use that for that reason. The standard deviation is a very good measure of how spread it out is. Right now, we'll just tell you, you know, big is worse, right? A big number means it's really spread out. A standard deviation that's a small number is, you know, pretty tight, right? The data's a lot. And the interquartile range is very nice as well. So these 2 are good. We use them a lot. And this one we actually use the most by far. Now, I had 2 guys, didn't we? So the data that we got for guy A, let's do a little table so we can compare them, and guy B. And we got a range, and we got standard deviation, and we got the interquartile range. And guy A was pretty consistent, wasn't he? Right? Didn't vary too much. And the numbers we got were 10 to 2 decimal places, 4.47 and 5. Right. Now this time I'm just going to use my calculator. And here goes. Start button, number 1, edit. And then just hit a load of deletes till that goes away. And then while I'm at it, a whole load of deletes to make everything go away so I'm not distracted. Right. And now I'm going to put all my data in L1. So what's that going to look like? Oh, here it is. It's going to be 10, 20, 50, 20, and 10. Right, so there's the data in. Start button again. Move over to calc and 1 variable statistics. Now, do you see I've got the old calculator, right? In which case I need to tell it L1. So blue button 1, and then I can hit enter. And the standard deviation is now this guy. What's that? About 16.43. If I scroll down, I can now see that the maximum was 50 and the minimum was 10, so that gives me a range of 40. And the interquartile range would be Q3, which is 35, take away Q1, which is 10, 35 take away 10, leaves me with 25. Can you see that these measurements indicate what we already could tell just by looking? Isn't player B much more inconsistent? Isn't his scores vary a lot? Isn't player A much more consistent? To finish with this question with a kind of sports situation, can we just pretend that you are a manager for a basketball team and you've got all your players picked and you're really only going to pick one of these two players? And the next game you're playing is a big game, right? If you win this game, you're into the finals, right? And if you lose this game, that's the end of your season, right? So you only have one guy to choose. And the question is, who should you choose? Who are you going to pick, Zach? You're the manager. A or B?
Probably A because they're more consistent.
And consistent is safe. Agreed? If you play A, you're going to get 20 points anyway, right? And you might get 30. And if you look at the team that you've played against and you know enough about their statistics, couldn't you make an intelligent guess on, yeah, I'll probably beat that team, maybe only by 5 points, but I know that the other players I've got will get this many points, and I know the kind of players they've got, on average, they'll get that number of points, right? They do that numbers game, right? For instance, people who bet on gambling, don't they take that kind of data into account when they're trying to figure out who's going to win, right? And I would agree with you. I would think that would be your best guess or your best choice. So
You ever
let me
seen that
give-
movie Moneyball with Brad
No.
Pitt? That's what that's about. They use statistics to build a team for the Oakland A's, and they end up winning a World Series doing exactly what you're saying.
Interesting.
Pretty cool.
Here's my new analogy. Do you remember the story we talked about last game? You've looked at the data. That team's going to beat you. If you play A and only get 20 points out of them, they're going to beat you by about 10 points, right? On average, right? Sometimes you'll still win, right? Nothing's perfect. Why should you pick B in that case?
Because though there's lower consistency, there's a chance of a higher percentage point than A would ever get.
So if he plays a good game, right? 1 out of 5 is a really good game for him, right? Won't you actually win? So sometimes don't you have to gamble if you're a manager? Play safe if you know everything's on your side, right? We've got better points, better defense, better whatever it is. On average, 9 times out of 10, if I play A, we're safe, right? And that's the best bet for you, right? But if you're playing some team that you know is just better than you, right? They're going to beat you on average 9 out of 10 times. Don't you throw a curveball and say, okay, in you go, Joe. I hope this is the day that you play a great game. Now, if he plays a normal game, right, you'll get beat. But when you're going to get beat anyway, if you played Mr. Consistent, right? So that's the risk you play. So things like that get factored in, and they are very important, not just in sports, but you can think of a business analogy, right? What product should I be bringing out, right? Anything at all. You can analyze it in consistent, inconsistent. And that was a good question. I like that question, even though I made it up. I think it was a good question. Any questions so far about calculating, using your calculator, the 3 measurements, range, standard deviation, or interquarter range? Are you comfortable about how you would do it on your calculator? Right. So the second version of that is, how do you do the same calculation using salt? So I'm kind of loading up salt as we speak here, and hopefully I can get one. Here we go. I've got one. Oh, if you're getting in chat, I should be reading. Oh, somebody mentioned that was a great movie that you were talking about, Zach. What's it called again? I'll have to look it up.
It's called Moneyball with Brad Pitt.
Oh, Brad Pitt. I'm sure my wife likes Brad Pitt, so I could probably get her.
Yeah, most of them do, right?
Yeah, sometimes you have to do that if you want to, if I want to watch a movie, I'll say, Brad Pitt's in it. Oh, okay, we'll watch it,
Sell it to them a little bit.
Yeah, you have to, you have to figure out things. You'll know that. You're married, so you know how to do this, right?
Yeah.
Got to get this out of my head because I'm distracted when a thought comes into my head. My wife does like a lot of the movies that I like, which is really good, right? We both like sci-fi movies, right? For instance, that's one of the main things I like watching. So does my wife. So we don't really have a problem when there's a sci-fi, but my wife likes romantic comedies.
Ugh.
I exactly. Not my favorite, right? I know, but I like war movies and she doesn't. So there's this kind of compromise. You're going to have to watch this war movie and I'll watch this romantic comedy, right? You see, that's how you
That's a
live
fair
when you're married, right?
Seems like
That's
a
the
fair
fair
trade.
trade. So getting to the bottom line of this story, my wife said, oh, I'm getting the movie, right? I'm doing the movies this week, right? So we went to a movie and I said, what's this movie like? She said, well, it's not a romantic comedy. And I thought, whew, dodged a bullet there, right? And she took us to a disaster movie, I'll call it, because she loves disaster movies, and I'm not really keen on them either. You know, the one where everybody dies except the two people that you know are going to live right at the start, right? You always know the evil bad guy's going to get killed by a rock hitting him or whatever the disaster movie's about. So you already know the storyline, so that's what bores me. Anyway, she said, oh, it's a kind of disaster movie. I thought it's great. And I think it was called The Greatest Storm or The Big Storm or something. I don't know if you know the movie.
Yeah.
And that was the most depressing movie in the world. Everybody drowns. Everybody drowns. And I'm trying to figure it. That's a depressing. At the end of the movie, at least you got a couple of people. I'm glad they made it out alive. The volcano didn't kill them. No, they died. All the people you thought were going to died as well. Helicopter guy coming to save them died as well. I'm thinking, what the bloody movie was that?
Sounds like a
for,
depressing movie.
It was just a depressing movie. So you got to be careful when you make deals to maybe look up the movie and say,
Know what you get yourself into.
Yeah, can we not just watch a romantic comedy instead?
There's got to be some rom-com war movies.
Thank you. Yeah, okay. Look, God, I apologize, but if I don't get things out of my head, they just distract me. So, right, you should now be looking at use a salt button, okay? And here is our data set. Right? And we are going to use our data set. And they are calling it little s. Do you see that? I would call that standard deviation. Okay, so use your calculator to get little s. Well, we know how to do that, right? But here is a data set. Let's use salt. So click on salt. There we go. We're going to use it to calculate the standard deviation. So there's the numbers, not really that big. If you go to descriptive statistics, isn't it nice when they call it something that you can read? S is standard deviation. Now, if I was writing that question, wouldn't I probably have said, use salt to find standard deviation? Isn't that a lot clearer than use salt to find S? Right, but yeah, okay. Got over with. 3.32. Gotcha. Copy. .32. Now, if you add 7 to all the data points, so add 7, add 7, add 7, add 7, add 7, right? You've done it to all of them, right? Recalculate the standard deviation. Now, I'm going to go back to the data set that we have, and I'm going to add 7 to each of them. So that's now going to be 19. Now I'm going to add 7 to this, and that's going to be 13. Well, if I do it right, it is. And if I add 7 to this guy, it's going to be 15. And I'll add 7 to this guy, and it's going to be 13. And then I'm going to add 7 to this guy, and it's going to be 11. Now, if we were doing the question, what would the mean, mode, and median be? Wouldn't I just add 7 to all the numbers, and that would have been my answer? And it works, right? Remember, if you add 7 to all the data, doesn't the mean increase by 7, the median increase by 7, and the mode would increase by 7? What do you think happens to data if you add 7 to all the numbers? Are they any more spread out than they were before I added 7 to all those numbers? What do you think? Because we're about to do it, but what do you think?
I don't think they're spread out. They just have a higher value, right?
Yeah, and so they're not any more spread out. Shouldn't I get the same answer that I got a minute ago, which is what, 3.5716 or whatever it was? Let's find out.
3.32.
3.32. So hit that guy. Copy it. Oh, now, oh, shooting space. Did the data set change there? Yeah. Can you trust me? These two numbers should have been the same, but I've probably added 7 to one of my data points wrongly. Right, because they should be the same. Let me just do this as a double check. 126864. Right. 126864. Okay, gotcha. Descriptive statistics. Ah, there you go. I don't know where that number came from, but isn't it the same number in both cases? So here's a difference. If you add the same number to your data set, your standard deviation doesn't change. Neither does your range, and neither does your interquartile range. None of them change. Interesting. So if you take a data set and you add the same number to all the data points, none of those measurements of variation change, right? Range, interquartile range, standard deviation. What do you think would happen if I took the data, right, these numbers, and didn't add 7 to them? We've done that and it doesn't change anything, but I doubled them. So I made every number twice what it used to be. What do you think would happen to all three measurements of variation?
Will it just double it?
What do you think, guys? Does that seem reasonable?
Instead of 3.03, it'd be 6.06.
Yeah, I would agree to that.
Good, because that's exactly what happens. So I've changed all the data, right? So I should just go up here, and there you go. I know this isn't the place to put the data, but can I just put it there so we can see the before and after? Would you agree it just doubles it? So doubling your data doubles your variation, right? They become twice as spread out. That makes sense? And interquartile range, the same thing happens. And what we call range, same thing happens, right? So if you treble the data, or if I say triple the data, you get 3 times what you used to have. If you half the data, won't you half the variation? So this, no matter which one of the 3 different ways of measuring variation that you have, do you see that you basically don't get any change if you add or subtract? And if you multiply by 8 or 2, then that's what the guys are like, and that's essentially what question 6 is like. So I'm now going to show you some special data sets and see if you can predict what. We'll use standard deviation, but it doesn't matter. All three do the same thing. Here is a very boring data set. Right, you couldn't get any more consistent than 5s all the time, right? What do you think the number for the standard deviation should be if all the data is the same number?
0, wouldn't it?
It would be, and good news is, it is. And the interquartile range, if you do it, is 0. And if you want to find, you know, big take away small, it is 0. Isn't that nice that the number that we use to measure variation gives you values that kind of make sense, right? If I say the standard deviation is 0, you're going to say, oh, that data is the same number all the time. Every one of them's the same. Because doesn't that mean there's no variation? No variation, 0. Make perfect sense. Is there any limit to how big standard deviation or any of the others can be?
Be 100, wouldn't it?
Well, if it was a percentage scale, you might think that, but couldn't you just have number that was millions and millions apart? Like you're measuring distances between, you know, solar systems or something, right? So theoretically, your variation could be as much as you like, right? It could be any number, but you'll never get negative, right? That wouldn't make sense. 0 is the smallest. Are we good so far? Right. Now I'm going to show you some, we'll do some notes for a while. Standard deviation being used in a couple of ways, and I'm going to show you interquartile range after that being used in certain ways. So imagine that I have some data, and I'm not going to write them down this time, but the mean in a test was 57, right? So suppose the teacher gave a test and the average for all the students who did the test was 57, right? And the standard deviation was 5. Now, there are a couple of things you can do when all you're told is those two things. For instance, I can tell you whether someone's score would be considered an outlier, right? Somebody who got exceptionally big or exceptionally small, right? I could tell you what an outlier is. So here's your test for an outlier. It's the mean plus 3 standard deviations. And if that's true, if it's bigger than that guy, it's an outlier. Or if it's the mean, take away 3 standard deviations. If it's less than that guy, it's an outlier. So let's find out what those are equal to. The mean plus 3 standard deviations is 57 plus 3 lots of 5, which is 15. So that's 6, 2, carry 1, 2, 72. And that guy is 57. Take away that amount, 15, that leaves me with 42. So the test for an outlier is, if you're bigger than 72, you are an outlier. Or if you get a score less than 41, or 42, I should say, you're an outlier. So suppose someone said to you, James got 80. Janice got 40. And Robert got 70. Is James an outlier?
Yes.
Yes. Is Janus an outlier?
Yes.
Which means that they are exceptionally good or did exceptionally bad, right? Most people in the class don't get those kinds of scores, right? In this particular test. Now, what about Robert? Is he an outlier?
Not quite.
No. He did good, right? We're not arguing he didn't do good, but he's not an exceptional outlier, right? We cool about that? Now, suppose I tell you that the median, right, the middle score, or yeah, the middle height was 60. And that the interquartile range was 6 inches. So we measured the heights of various players in our team, and the median height was 60 inches and the interquartile range was 6, because these are small people, because they're, you know, junior high or whatever, right? They're not big adults, right? There is a test for outliers in this situation as well. You get the median, med for short, plus 1.5, I know it's a weird number, interquartile range. And you do the median, and I've just said median. You do Q3, add 1.5, and you do Q1, take away 1.5 interquartile range. Of course, for me to tell you that, I now need to tell you what number Q1 was and what number Q3 was. So, yeah, these are the two numbers I need. Now, so Q3 is 64 plus 1.5 interquartile ranges. So that's 9, so that gets me 73. And Q1 was what, 58, and you take away 1.5 interquartile ranges, and that's what, 6, that's 9, so you get 49. So these are the extremes. You are an outlier if you're bigger than 73 inches, right, which is what, 6'1", and you are an outlier if you're under 49 inches. So these kids, if you're less than 4 feet, you're pretty much an exceptionally small person for that age group. And if you're 6 foot and a bit, right, you're exceptionally tall for that age group. So we have 3 people, I'll call them A, B, C. One of them is 47 inches tall. One is 71 inches tall, and the other is 75 inches tall. So here are 3 students at this particular team. 47 inches. Is that person considered an outlier for this data set?
Yes.
Right. Less than 49 or bigger than 73. So that's a yes. What about this person who's 71 inches? That's a no, isn't it? And lastly, what about a 75-inch person? Well, that would be a yes, isn't it? So we can tell whether a person is exceptionally big or exceptionally small. That's what an outlier is. And all you need to do is tell me the mean and standard deviation, or you need to tell me the median and these 3 guys. Are we good? Any questions so far? Seeing if yeah, I've got it. Right, I wanted to show you, I didn't know if it would have it, and I'm glad it has. I wanted to show you why we don't do standard deviations by hand. So are you looking at this screen here with a funny sigma and a whole load of square roots? Here, up here, God, miles away, here is the data set. It was only 5 numbers, right? Not the biggest data set in the world. You find the mean. You subtract each number from the mean. You square each of these numbers. This formula here basically says add up all these numbers and don't divide them by 5, which is what you think you should divide them by. Divide them by 4. And if that wasn't bad enough, take the square root of the answer. Can you see why you don't do these by hand? That's just for 5 numbers. Imagine it was 15 numbers. Right, when you have to take a day off work just to do it, right? You would be here all day. So we are happy, I hope, that, have I convinced you at least that you don't want to do it by hand, right? Which is kind of what that was for.
I had to do it by hand once in General Kim, and it was not.
Oh God, who did that to you?
I just didn't have my calculator.
Oh, okay. No, but did you say someone got you to do it by hand?
Oh no, our assignment was due the next day, so I was sitting there all night working.
Oh God, you poor soul. Okay, so next I'm going to tell you about a guy. I'm having to read it because I can't spell his name. Chebyshev's theorem. And what he said is that if you want to calculate essentially, how would you call it? That for any set of data, for any constant k greater than 1, the proportion of data that must lie within k standard, I better write this down, I'm writing it here and it don't make sense to me, right? For any set of data, the proportion of data, but to write in the rest now, that lies within k standard deviations of the mean is at least 1 take away 1 over k squared. Okay, there's Chebyshev's, there we go, Chebyshev's theorem. So let's say that I have done a test, an IQ test, and the average was 100, which actually that's what the typical IQ test average is, right? It's 100, right? So I did it with all the students that I teach, and I got an average of 100, and I got a standard deviation of 10. Okay, I would like to know what percentage of my students are within how many standard deviations do I want? Are within 4 standard deviations of the mean. Well, let's see what that looks like. You take the mean and you do plus or minus 4 standard deviations. That's what it means when you say are within 4 standard deviations of the mean. So 100 plus or minus 4 times 10, which is 40. So that would be an IQ of 60 up to an IQ of 140. I would like to know what percentage of my students will have an IQ in the range 60 to 140. So we need to know what K is. In my story, K represents how many standard deviations away from the mean you are. In this case, wasn't it 4, right? So K is 4. What percentage of my students? 1 take away 1 minus K squared. 1 take away 1 over 4 squared. 1 take away a 16th, which I'm now going to convert into a decimal. 1 take away 1/16. And the decimal I got is 0.9375. And I prefer, as most people do, percentages. So I can tell you right now that if the mean was 100 and the standard deviation is 10, then the number of people within 4 standard deviations of the mean, which is between 60 and 140, 93.75% of my students will be in that range, at least that amount, maybe even more. To see that we can now use the standard deviation to give you ideas about what the intervals, various intervals would look like. Right. Let's do another one. Let's suppose that I gave a quiz and the average was 50 and the standard deviation was 6. And I want to know what percentage of my students would be within 2 standard deviations of that mean. So let's see what that looks like. Plus or minus 2 standard deviations. So that means K equals 2, right? 2 standard deviations. So it's 50 plus or minus 2 lots of that is 12. So what percentage of my students would get a score from 38 to 62? Well, according to Chebyshev, it's 1 over 1 minus K squared, 1 over 1 minus 2 squared, 1 minus a quarter, 0.75. So the answer is 75% of my students would have a score in that range. So what this is saying is, if you know the mean and standard deviation of your data and you don't know anything else, right? Because the person who gave you that information didn't tell you anything else, can't you still do these calculations and find out how much of the data is in this range, how much of the data is in whatever range you could possibly think of? It's pretty impressive that you are able to do that type of thing. Are we cool on that? Now let's show you another guy, another thing that you can do with this data. Oh God, what's the time like? When are we meant to finish here? 25 past? 35 past? $25 past. Yeah, I got enough time. Let's go for it. It's a very short thing, so here we go. So the thing that we're going to show you how to calculate now is called the coefficient of variation, called CV for short. And you calculate the coefficient of variation by taking the standard deviation and just dividing it by the mean, and then you multiply the answer by 100 because the coefficient of variation is a percentage. So suppose I had a mean and the mean was 52 and that the standard deviation was 6 and I would like to know the coefficient of variation, you would take 6, divide it by 52, and then multiply it by 100 to get a percentage. So I would just go to my calculator and I do 6 divided by 52 and multiply that by 100, and to one decimal place, that is 11.5%. And so this is just another measurement of variation. Now, what makes this a little bit different from the others is, do you notice that this particular measure of variation uses the mean and the standard deviation together? And that's quite helpful, because you know, when you had data that was the same variation, but weren't the numbers totally different? One could be huge, big numbers, but they're the same distance apart, and some were very small numbers in the same distance apart. Can you see in those cases, you couldn't tell which was which because the number would be the same for standard deviation and so on? Because you use the mean of the data in this calculation here, and what that does is it takes into account how big the numbers are as well as how varied they are. So it kind of does a little bit of both. You know, if you have a coefficient of variation that's 0, doesn't that mean that there's no variation in your data? Right, they're all the same number, so that works. And what's the worst you could expect? Well, there isn't a limit like, oh, well, 100% is the biggest. Theoretically, you could get that, but you would typically expect this coefficient of variation to be in the single digits. Now, there are certain people who use this. People who are into the stock exchange, for instance, like to use all sorts of numbers to tell them what's going on, right, with the price of stocks, you know, S&P, whatever it is. And one of the numbers, these are called statistics. Anything that you get from data is called a statistic. The coefficient of variation is sometimes used, as it gives them a good measurement of how much volatility there is in a market, right? You know, so if the CV for the stock exchange is normally 4%, which I don't think it is, but let's say it was, if one day it's 44%, isn't there some weird stuff happening in the stock exchange, right? They're buying and selling all over the place, right? Nobody knows what the heck's happening, right? If the CV is 1%, wouldn't you be in a very stable market, right? The prices aren't shifting that much, right? A 1% CV is a very stable market. Into double digits is a bad market. Bad market for predicting what's happening, right? And that is a good point for us to say, put your last name down and we'll call it a day.